So now that we're familiar with how to analyze our ideal op amps, what we're going to look at is a few different configurations over the next several videos that commonly come up. And what we want to do with these configurations is we want to find some general equation for our closed loop gain. So our goal here is we want to find a general equation for our closed loop gain. And so remember, our closed loop gain is A sub C. And so the reason we might want to do this is instead of having to do this analysis each time, we can say, oh, this is this configuration. Let me go to my equations. So the first configuration that we're going to look at is actually the same one we just looked at in our previous video, and it's something called an inverting amplifier. And so like I kind of talked about in the previous video, we can see that's because our input, in this case V sub I, is connected indirectly through resistor R1 to our inverting terminal. Okay, so let's go ahead and get started here. So we're going to, this first time, use our ideal op amp sort of properties. So we can say we have zero current into our ideal op amp. So that means that we have zero current here and zero current here. So let's go ahead and label some of our other currents. So let's say, for instance, we just call this I sub 1 and we call this I sub 2, just to be consistent with our notes. Okay, so if we have I1 and I2, we can say from KCL, because we know that there is zero current into our ideal op amp terminals, we have I1 is equal to I2. Okay, so now we're going to need to use our other property of our ideal op amps in order to find our relationship. And we do that by remembering that our VD, our differential input voltage, is 0. So because of that, we can say that our inverting terminal is at our virtual ground. So inverting terminal, which is the one on top in this case, at virtual ground. And so remember, we talked about last time, what that means is there's no physical path to ground, but it's essentially at a ground potential. And the reason is because our inverting terminal is connected to ground. If the difference between the two input terminals, the voltage has to be 0, that means that this point is also at 0. And so we could also draw that as this point here, we have V equals 0. So it's essentially like having a virtual ground there. So we could draw out our more detailed voltages with polarities if that's helpful. We could write this as VI, and we could write this as V out. So of course now we can use our Ohm's law to write our currents in terms of the voltages. So our I1 is just going to be equal to VI divided by R1. And then we have our I2 is going to be equal to negative V out over RF. And so we have to remember to keep passive sign convention in mind. So the reason we had this negative sign, if we come back up here, we can see our I2 is going through a voltage rise in that reference polarity, indicating we need a negative sign for any equations relating current and voltage. And in this case, we're using Ohm's law, which of course relates current and voltage. So now if we use these three equations here, combine those, what we're going to get is our VI divided by R1, sorry, this should be R1 here, not RI, is equal to negative V out divided by RF. Rearranging, of course, we can solve for our closed loop current gain, which in general is defined as output voltage divided by input voltage. So in that case, this is going to be negative RF over R1. So we could write this answer in terms of our closed loop voltage gain, or we could write in more general terms, V out is going to be equal to negative RF divided by R1 times our input voltage VI. And so this is going to be a useful equation to know, because whenever you see an inverting amplifier configuration, we can go directly to this equation. We identify, well, our RF is this feedback resistor that's connecting our output and input. Our R1 is connected to our input. plug them into their respective places, and we can find out what our output voltage is for any given input voltage. So a few things we want to note about this relationship here for this inverting amplifier. So let's just say some notes here, items of interest. So our output polarity is going to be opposite compared to our input polarity. So opposite polarities on input and output. And so of course that's as we would expect because we are calling this an inverting amplifier, and of course where this shows up in the equation is this negative sign here. And so this is maybe easiest to see if we're talking about some time varying signal. So maybe as our input we have something that looks like this. So it's going up, down, the way I've started it. So then our output would be going in the opposite direction. So it would be going down, then up, and down, then up. And so it's kind of hard to tell with my poor drawing skills, but we'll see this a little easier in a later demo in PSpice. But basically we've just shifted this wave 90 degrees. And of course if we have a DC input, it's just going to switch the sign of it. If the input is -2, the output is going to be positive and then multiplied by this factor RF over R1. Okay, so another important thing to note looking at this equation is that our closed loop gain, A sub C, and so remember we can write V naught equals negative, not negative, we can write V naught equals AC times VI. So our AC is the negative RF over R1. That value, our closed loop gain, A sub C, only depends on external resistors. And by external resistors, I mean resistors that are external to the op amp. So external resistors. And so what that means is we have a lot of design freedom in terms of choosing values for RF and R1 to amplify by how much we want. But we need to keep in mind, like I said way back in our first video, that we're going to have this saturation effect come into play based on the biases used to bias or power our op amp itself. And then one last note is just where are these inverting amplifiers commonly used? Well, they're commonly used when we want to do a current to voltage conversion. So current to voltage converters will typically use these inverting amps, but we'll see some other functions where we can use these as well. Okay, so that's all for this basic introduction. The next thing we'll look at is an inverting amplifier example, and then we'll get into some other types of amplifier configurations.